Hi, welcome to this session on Mathematics, Chapter 1 Real Numbers for Grade 10, Section 1.5 Revisiting Rational Numbers and Their Decimal Expansions, Theorem 1.5 and 1.6. But before we proceed ahead, remember that a rational number can have either a terminating decimal expansion or a non-terminating but repeating decimal expansion. Example would be for the terminating decimal expansion would be 5 divided by 2, which is equal to 2.5, and the example for non-terminating and repeating example would be 1 by 3, which is equal to 0.333, and so on. For the first part, which is a terminating decimal expansion, we have theorems 1.5 and 1.6, and for the second point, for that is non-terminating but repeating, we have theorem 1.7. So what do these theorems say? So theorem 1.5 states that let x be a rational number whose decimal expansion terminates. So this is an important word here. Then x can be expressed in the form of p divided by q, where p and q are co-primes, and prime factorization of q is of the form 2 raised to power n multiplied by 5 raised to power m, where n and m are both non-negative integers. And theorem 1.6 states that let x be equal to p by q, a rational number, such that the prime factorization of q is of the form 2 raised to power n multiplied by 5 raised to power m, where n and m are non-negative integers. Then x has a decimal expansion which terminates. So now let's take some examples which pertain to theorem 1.5. Let's consider 0.375, which is equal to 375 divided by 1000, which can be factorized and can be written as 3 multiplied by 5 raised to power 3 divided by 2 raised to power 3 and 5 raised to power 3. Now we can cancel out the common ones. 5 raised to power 3 goes out, and we are left with 3 divided by 2 raised to power 3. Similarly, 0.104 is equal to 104 divided by 1000, which can be written as 13 multiplied by 2 raised to power 3 divided by 2 raised to power 3 multiplied by 5 raised to power 3. And now we cancel out the common factors. In this case it is 2 raised to power 3 and 2 raised to power 3 goes out here, and we are left with 13 divided by 5 raised to power 3. Similarly, 0.0875 is equal to 875 divided by 10,000, which can be written as 875 divided by 10 raised to power 4, which is equal to 5 raised to power 3 multiplied by 7 divided by 2 raised to power 4 multiplied by 5 raised to power 4. And then we will be left with, after cancelling the common factors here, we are left with 7 divided by 2 raised to power 4 multiplied by 5. And now let's take another example. 23.3408 can be written as 233408 divided by 10 raised to power 4, which can be written as 2 raised to power 6 multiplied by 7 multiplied by 521 divided by 2 raised to power 4 multiplied by 5 raised to power 4. Cancelling out the common factors, we shall be left with 2 raised to power 2 multiplied by 7 multiplied by 521 divided by 5 raised to power 4. Now if you see here carefully in this box and this box, we can say that for any real number which has a decimal expansion that terminates, that number can be expressed as a rational number whose denominator is of the power of 10. So if you see here, we have converted all of them into the denominator with a power of 10. We know that only prime factors of 10 are 2 and 5. Hence, by cancelling the common factors in the numerator and denominator, we can say that the real number can be expressed in the form of p divided by q, where prime factorization of q is of the form 2 raised to power n multiplied by 5 raised to power m. And if we were to state this more formally, we can write the theorem 1.5 again, and I'll repeat it here. That theorem 1.5 states that let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p divided by q, where p and q are co-prime numbers, and the prime factorization of q is of the form 2 raised to power n multiplied by 5 raised to power m, where n and m are non-negative integers. Now let's take a few more examples for theorem 1.6. Let's take 3 divided by 8, which is equal to 3 divided by 2 raised to power 3, and now we convert the denominator into the power of 10 by multiplying and dividing by 5 raised to power 3 here, and we get 375 divided by 1000, which is equal to 0.375. Similarly, let's take 13 divided by 125, which is equal to 13 divided by 5 raised to power 3, and if we convert the denominator, which is this here, into the power of 10, we get 2 raised to power 3 multiplied by 13 whole divided by 2 raised to power 3 into 5 raised to power 3, which is equal to 104 divided by 1000, which is equal to 0.104. Now another example is 7 divided by 80. We can write it as 875 divided by 10 raised to power 4, which is equal to 0.0875. And the final example for now is 14588 divided by 625 is equal to 2 raised to power 2 multiplied by 7 multiplied by 521 whole divided by 5 raised to power 4. And if we convert the denominator, this is the denominator, into the power of 10, we get 233408 divided by 10 raised to power 4, which is equal to 23.3408. And now let's focus on the values which are in this box here. They are all having a denominator in the power of 10. So it appears that we can convert a given rational number of the form p divided by q, where q is of the form 2 raised to power n multiplied by 5 raised to power m, to an equivalent rational number of the form a divided by 10 raised to power c, that is a denominator is having some power of 10. And more formally, if we state, we will arrive at the theorem 1.6's text, which states that let x be equal to p divided by q be a rational number such that the prime factorization of q is of the form 2 raised to power n multiplied by 5 raised to power m, where n and m are non-negative integers. Then x has the decimal expansion which terminates. So this is the important thing, that x has the decimal expansion which terminates.